Let's start with this one simple example. I want to look at this system. X prime of t is the matrix 5, 3, negative 6, negative 4 times x of t. That corresponds to the system x1 prime of t is 5 x1 of t plus 3 x2 of t, and x2 prime of t equals minus 6 x1 of t minus 4 x2 of t. How are we going to solve this system? Well, of course, that will mean we need to first find the eigenvectors and eigenvalues for this matrix A, which is the matrix 5, 3, minus 6, minus 4. Well, to find this, we need to look at the characteristic polynomial, which is the determinant of this matrix A minus lambda I. That's the matrix 5 minus lambda, 3 minus 6, and minus 4 minus lambda. And that's just 5 minus lambda times minus 4 minus lambda minus negative 18, which is plus 18. And that's equal to negative 20. Then we have plus 4 lambda and minus 5 lambda. And then we have plus lambda squared plus 18, which we can write as lambda squared minus lambda minus 2. And we can easily factor that as lambda minus 2 times lambda plus 1. That tells me that lambda equals 2 and lambda equals minus 1 are the eigenvalues. Those are the roots of this characteristic polynomial. We then need to find the eigenvectors. To find the eigenvectors, for example, corresponding to lambda equals 2, we want to solve the equation A minus 2 times the identity. I should use a different letter here, times v equals 0. And how do we do that? Well, A minus 2i has the matrix 3, 3, minus 6, minus 6. So in order to solve this equation, I can look at the augmented matrix. That looks like this. You put the matrix for the matrix A here, 3, 3, minus 6, minus 6, and then our 0, 0 here from the 0 vector, and I do Gaussian reduction, which is trivial here because the second row, when I add to it twice the first row, zeroes out, and I get 3, 3, 0 on the first row, which I then divide by 3, and I can get 1, 1, 0 on the first row, and 0, 0, 0 here. Remember, if we're thinking about v as the vector v1, v2, I should write it like that, then this first column corresponds to v1, the second column corresponds to v2, and this just says that v2 is minus v1. Or I should write v1 is minus v2, and then I can write v is minus v2, that's v1 and v2, which is v2 times the vector minus 1, 1. What does that tell me? That tells me that this vector, minus 1, 1, is an eigenvector for the matrix A corresponding to lambda equals 2. Any non-zero multiple is also good, but we'll just use this one. And of course we can check this. Take our original matrix A, 5, 3, minus 6, minus 4, multiply it by minus 1, 1, and what do we get? We get negative 5 plus 3 is negative 2 for the first entry, and we get 6 minus 4, which is 2 for the second entry. That's twice our original vector, and that tells me, yes, we have an eigenvector with eigenvalue 2. We also need to find the eigenvectors for eigenvalue 1. And I'll leave you guys to do the work there, and I'll just tell you that the vector -1, 2, and you can check this really quickly, probably in your head. You can see that this is, in fact, an eigenvector for eigenvalue 1. And, in fact, it will be the only one. The general theory of eigenvalues here for matrices tells us that when we have single roots of the characteristic polynomial, these are not roots of higher multiplicity, then we're going to have at most one independent eigenvector for each eigenvalue. When you have a root of higher multiplicity, say multiplicity 4, if the characteristic polynomial has a high degree, that might be possible, then you can have either one independent eigenvector for that eigenvalue, or possibly 2, 3, or 4, up to the multiplicity of the eigenvalue of the eigenvalue's root in the characteristic polynomial. So I had said before that -1, 2 is an eigenvalue for lambda equals 1. If I just multiply that by 1, I can certainly use 1, -2, which is what I seem to have used here. If this is an eigenvalue for lambda equals 1, any non-zero multiple is, so we can use this one instead. So I'm just now asking you to solve this problem. We have the same a system of linear differential equations. X prime of t is this matrix A times x of t, only now I'm giving you an initial condition, x of 0 equals -3, 1. Remember, I'll rewrite that. That's saying to solve this system, x1 prime is 5x1 plus 3x2, x2 prime is -6x1 minus 4x2, and saying that the vector x at 0 is -3, 1 means x1 of 0 is -3 and x2 of 0 equals 1. By our general theory for the existence and uniqueness of solutions to linear systems of differential equations, we know there should be a unique pair of functions x1 and x2 which solve this system and have the correct initial values here. What is our general solution to this equation? Well, we know that e to the minus t, e to the -1 times t, that's for lambda equal to -1. Oh, sorry, this was lambda equal to -1 here. This was for lambda equals -1. We have e to the minus t times this eigenvector 1, -2. And for lambda equals 2, we have this eigenvector -1, 1. So we know that e to the minus t times this eigenvector is a solution. E to the 2t times this eigenvector is a solution. Any linear combination will still be a solution, and in fact the general solution will be the set of all linear combinations. So the set of linear combinations of these two solutions looks like C1 times the first plus C2 times the second. And when I just write that out component-wise, I get in the first component C1 e to the minus t minus C2 e to the 2t, and in the second component minus 2C1 e to the minus t plus C2 e to the 2t. And that first component is what we're calling x1 of t, and the second is x2 of t. So here we're solving the same differential equation. Here's the general solution. To find the ones that have the correct initial values, remember we need x1 of 0 is -3, and x2 of 0 has to be 1. We just solve x1 of 0 is c1 minus c2, that has to be -3. x2 of 0 is 2c1 plus c2, that has to be 1. So we solve this system of two equations in two unknowns, and it's very easy to solve that system. You can check very quickly that c1 equals 2 and c2 equals 5 certainly makes the first equation true, and it also makes the second equation true. You can come up with this just by adding the two equations, and right away you'll get, when you add the two equations, you'll get minus c1 equals -2. That tells you c1 equals 2, and you can plug that in to get c2 equals 5 very easily. So when we put those in, we get our final solution. x1 of t is 2 e to the minus t minus 5 e to the 2t, and x2 of t is -4 e to the minus t plus 5 e to the 2t. Do you think it's worthwhile checking such a solution? The answer is you'd better check, because it's very easy to make mistakes here. So what do we need to be true? We need x1 prime to be 5x1 plus 3x2, and we need x2 prime to be minus 6x1 minus 4x2. And we need x1 of 0 equals minus 3 and x2 of 0 equals 1. Well, it should be immediate that x1 of 0 is minus 3. You just plug in 0, you get 2 minus 5 is minus 3. And x2 of 0 is minus 4 plus 5, that's 1. So this part checks really easily. We just compute x1 prime. That's minus 2 e to the minus t minus 10 e to the 2t. And x2 prime is 4 e to the minus t plus 10 e to the 2t. So that 5x1 plus 5x1 plus 3x2 is 5 times this, that's 10, plus minus 12 is negative 2 e to the minus t. 5 times this plus 3 times that is exactly minus 10 e to the minus 2t. So this first equation checks, and I'll leave you to check this second equation. It will work out just fine.